All right, let's get started. Discussing transfer function, right? Transfer function of translational systems. That's what we discussed last time. What we'll do today is we'll look at electrical systems. Okay. Electrical network. Transfer function. Just like translational mechanical systems, we develop our electrical circuits around three main components. Okay, three main components of electrical systems. The first one is the resistor. Then you have this is inductor. The general term used for these elements is impedance. You know what impedance is? Impedance is general resistance to flow of electricity. Okay. One of the things you have to remember is when you're solving this relationship is very important. Ohm's law. Okay, Ohm's law says V is equal to IR, right? So what does this mean? This is specifically for resistance. Okay. If the element is a resistor, Ohm's law is V is equal to IR. Okay. If the element is a inductor, it is V is equal to L into Di by dt. And if it's a capacitor, it's V is equal to 1 over C integration of I Does this make sense? This makes sense? Yes. Okay. So what this means is, just pay attention for a minute. You have to understand what is the constant here. Think about LTI systems. Again, let's go to LTI systems. LTI stands for? We discussed LTI, right? Control systems, the control system, scope of the control systems for this course is only for LTI. LTI is linear time invariant. Okay. So again, linear means the input-output relationship is a straight line, and time invariant means the system does not change as a function of time. So what does not change here? No. Huh? The R does not change. Okay. See, V and I are variables, right? Depending on what kind of V you supply, you get a I, the current flow. But R is a system property. It's a property of the material, resistance. So that does not change. Now, is it a practical thing to assume that R does not change?
No.
Why not?
Because it heats up and the resistance
increases, right? So when you have any electrical system, you guys did the lab, right? The structures lab, and when you did the first structures experiment, we allowed the system to stabilize, which means when we apply voltage, current starts flowing. When current starts flowing, it heats up that particular element because there is activity, and when it heats up, this resistance slightly varies. Okay. So if resistance varies, what happens? Voltage is the same. Voltage you are not changing. So the current flow reduces a little. But for this reason, the reason why we allow the system to heat up is we say it will stabilize. So we know the resistance will heat up only to a particular value, and then there is almost a constant current flowing through the system. Okay. Even in this one, what will not change? L. L is the system property, inductance of the material. And here it is C, the capacitance. Okay. So these are the system properties which we assume will not change. That is for LTI systems. We have this. What you need to look at is, which is going to be most helpful is, remember impedance, we talked about impedance for translational systems as well. So the impedance for a resistor, Ohm's law, it is V is equal to R, G is equal to L di over dt, and V is equal to 1 over C. This and this, it's the same. Okay. So V and V of t should make sense to you always. If I write something like this without a t, you should know whether it's a function of time or not. Right? You should be aware by now. Now the next one is we are talking about impedance. Recall impedance when we talked about for translation. So the impedance for this is R. Okay. Impedance for inductance is Ls, and the impedance for capacitor is 1 over. Okay. These are the values which you need to really remember. That's how you are going to build your transfer function. What is the input? What is the output? What is the input?
Your input is what your oh, you talking about in relation
For any of these.
the input
cannot input a current,
Yeah, it would be the V.
right? How can you input a current? What is current? What do you understand by current?
It's a flow of something.
Flow of electrons, right? So there is a potential difference. What is the potential difference? What is, where do electrons flow? If you have this circuit, so you have voltage, okay? In which direction is the current going to flow? This way? You sure?
They flow negative positive.
Huh?
We have to define it sometimes, but this is battery.
Will the path flow through this?
Electrons are what? Negatively or positively charged particles.
Negative.
So they cannot flow in that direction.
Yeah, flow negative positive.
The electrons flow in this direction, the current flows in the opposite direction. You have to understand, because they have to flow from negative to positive. They are negatively charged particles, right? They cannot flow to the negative. They'll be repelled in that direction. So this is not a very it's not out there. You have to know this as engineers, so that electrons flow in the opposite direction. The current flows from positive to negative, but the electrons flow from negative to positive.
I never understood that. I said I never understood that. Could you elaborate on why the current flows in the opposite direction of the
What is current? Current is energy, right? So this it is just that when these flow, there is a transfer of that energy, that current, which skips. It's like there is nothing happening in that direction. Okay. So that's what you need to understand. Now, what is the input? The input is always a voltage. Voltage is potential difference. Okay. So input is this thing. Output is current. Current flow is the output. By controlling this input, you can vary the output. Okay. For example, you cannot input a displacement. Can you input a displacement? No, right? You can input a force so that something displaces. Similarly, you can input a voltage so that there is current flow. You cannot input a current. Alright? So this is your thing, and this is your impedance. Okay? These are the main things you need to remember. Now what you can do is you can play around with getting a relationship for I. So here this implies I is what? V over R, right? This implies L is what? Sorry, I is 1 over L integration of V. Something like that. Okay? So you can always play around these things, but the driving formula is this Ohm's law. Okay? Now when we are talking about simple circuits, via mesh analysis, so you'll be given a very simple circuit like this, plus so now you'll be given such a simple circuit, and then the question would be, find the transfer function. Let's say the transfer function here is V naught E over V or V naught of S over V. You have to understand something, and this I'm not going to explain this too often. When you apply a voltage, right? Is it visible? No? That's it. Okay. So when you apply a voltage, there's current flowing through this, right? You can measure voltage across these two elements and see that there is a voltage drop. Okay? You apply a voltage, that voltage is consumed by here. It's like applying certain energy. Okay? And that energy is consumed by this element. It's consumed by this element. And it's consumed by this element. So there's output voltage across these elements. And it's essentially just the output voltage would be, here would be L into di by dt. The output voltage here would be R into I naught or I. Okay, or here it would be V naught would be 1 over C into I. Okay. So when you're asked, you'll be given specifically to determine the transfer function for a particular element. Okay. Mesh analysis, this is equivalent to Kirchhoff's voltage law. Alright? So the voltage law says V of T is equal to V R of T plus V L of T plus V C of T. In this regard, V C of T, we are naming this as V naught of T. Alright? Think about, when you think about translational system, this is like the applied force. Applied force in a mesh, in a given mesh, is this. Okay? The input voltage is equal to output voltage across the different elements. Okay? Now what is V R of T?
That's the resistor.
R into I of T, right? Plus L into di over dt plus 1 over C into integration of this is the traditional way you're going to do it. This is what you are required to do for your first assignment. You don't have to use this. So what the first thing when you are given such a electrical circuit is you write the impedances. Okay, in your assignment or in your exam, what you do is you write the impedances. So what is the impedance for L? LS. What is the impedance for R? R. What is the impedance for C? 1 over CS. This is V of S. And this is I of S. Got it? So if you just do this again, you have V of S is equal to LS into IFS plus 1 over CS into. So let's do this as C. What is the transfer function here? The transfer function is,
I think you made a mistake.
huh?
So I think you made a mistake.
It is
Where you put the C, I think you put it on top.
this one.
No. You just corrected it. You said you changed the 0 to a C. The B to 0. You changed
Up
it to
top,
C.
up top.
Well, you have,
This one.
no,
Up.
right there.
You had to put 2 down up top. You put the C on the bottom.
Yeah.
It is V C of S over V of S, right?
Right.
Because we want output over input. So you have transfer function. This is how I do transfer function. The textbook is a little different. So what I do is I just do.
So question, do you want us to do textbook now, or?
You can do it either way. So V of S is what? I of S into plus R plus L of S, Ls plus 1 over CS. Okay? So now I have I of S over V of S is equal to 1 over R plus Ls plus 1 over. What do we need? We need VC of S. And what is VC of S? VC of S we need VC of S, which is 1 over CS into R. So what I do is I'll just multiply each side by 1 over CS. Okay? Or divide, let's call this A. A on both sides by CS. So what you're going to get is 1 over CS I of S over V of S is equal to 1 over CS into R plus L Now, this term, what is this term? VC of S, right? What we have is VC of S over V S is equal to 1 over RC S plus LC square Got it? Tim, you're with me? Okay. So any questions? So anything you're not following? So if I rewrite this, I want to write it as a quadratic equation, okay, or polynomial. Generally, you would want to write it as 1 over LC square plus RC plus.
So this is turning the electrical mesh into a transfer function.
What you would do generally is, see, if you're not taught Laplace transforms and you are asked to write this to develop the input-output relationship or the mathematical model of this, you would do this. So do you see this as a differential equation? You see a differential equation, right? You can look at this as either a first order or a second order because there is an integration here. If you take the derivative throughout, this will become a double derivative, right? So it will be a second order differential equation.
But how's that a second order?
Huh?
How's that a second order differential?
You have an integration here, right? So if you differentiate it throughout
To get rid of the interest.
to get rid of the integration, this will become di by c. This will become double derivative. This will become just a constant, or not a constant, but a 1 of c into is, and this will become again a derivative. So that throughout you'll have a second order differential. But you need not do that. What you can do is, if you are given for the course, you don't have to do this. Okay? So that's the reason I'm saying, if you are given a circuit, the first thing you're going to do is redraw the circuit in your assignment or exam and write the impedances. Okay? And then start with this. If it's Kirchhoff's voltage law, start with this. Input voltage is equal to output voltage for any mesh. Alright? So this is a simple circuit. What happens if we have a fairly complex so you'd want to do simple circuit via nodal analysis first before we go into complex circuit? Okay. We'll keep this. You are done noting this down? You ready to do this one for the nodal analysis? Shall I erase this whole thing? So again, it will be find the transfer function, but using Kirchhoff's current law. Find the transfer function. Same circuit.
It's really going down, and you feel crap.
Find transfer function via nodal analysis. And this is Kirchhoff's current law. So what does Kirchhoff's current law say? The current.
The sum of the current engineering node equals the sum of the current exponent.
Right. So if you pick any node, the sum of the currents entering that particular node is equal to sum of currents leaving that node. So what you're going to do is, for a simple circuit, it's generally very easy to pick that node. But if there are multiple loops in the circuit, you have to pick a node such that you get an expression for this has to be a part of the expression because we are looking at output of this, right? So the current entering here is equal to current leaving here.
So like you said, pick a node.
That will, we could have said, find the transfer function for this output. Here it doesn't matter because this will give you expression for either one of them. Or let's say if we said find a transfer function for this, if you pick this node, it's not going to, that expression is not going to have this term. So you're not going to get an expression for the output. So that's the reason you have to pick a node which will involve both the input and the output. Okay. So you have this node. Let's call this node 1.
So a node between the input and the output.
Hmm?
A node between the input and the output.
Something like that. So you have IR of S is equal to I C of S, right? You agree? This IR of S, when something is in series, what do you know about parallel and series circuits?
When they're in series, you can add resistors.
Correct?
Resistors straight across.
Right. What about the current? See, the current flowing through these is the same. Okay. So IR is the same as this. The voltage gets split for series. But if you're looking at voltages, so if you have this, the voltage across these is not the same. Voltage drop across this is different, across this is different, and total voltage, applied voltage is different. If you have something like this. Okay? The voltage gets divided. But what happens to the current? The same current is flowing. If you do this, the voltage across these two is the same. Okay, but the current gets split. So the current flowing through these is different from current flowing through this. The voltage across these two is the same.
So in series, voltage is divided
Voltage adds up, or
parallel.
right,
Yeah, so in pairs, the voltage stays the same.
right. In parallel, the voltage remains the same, but the current gets split. And here, the resistance is just the sum, right? Here it would be, if you have R and L of S, it would just be the total impedance would be R plus Ls. Here it would be 1 over R plus 1 over Ls. That's what you remember? This is how the resistance acts. Okay? So when you do this, you have to be careful with how you do this. So you have IR and ICS. Okay? So what you have here is V of T or V of S over R plus Ls is equal to V naught of T S VC of S into CS. Right? Now, we have V R over R. Yeah, good. Is equal to V C of S. This would be R plus VR would be V of S minus VC of S over R plus MS is equal to VC of S. If you reverse this, what you're going to get is V of S R plus MS is equal to VC of S into 1 over R plus MS plus 1 over. I'll explain to you, just give me a second. What you want to get here is Sorry. Yeah. This is R plus L is 1 plus T I think this is what you got for your first problem as well. Can you check the answer?
Yes,
Same, right?
yes, this is same.
Okay. So what do you do? Again, your first step is always replace the elements with their impedances. Okay. Now,
So what the elements
huh? With their impedances, right? So this is where you start. Is this clear to you? Okay. So this is current entering is equal to current leaving, right? This transition is it clear? No. The current, you have to look at the current between these two. Okay? So the current flowing is the same, right? Can you divide the voltage between these two and these 2 points? Or, right, distribute. See, voltage. Look at what did we say? Voltage input is equal to this plus this plus this, right? Now we are saying we'll do these 2 and this one. That's what we are interested in. Okay. If we call this as VR, the voltage between these 2 points as VR. Can you say V is equal to VR plus VC? You can say that, right? You could have said VL plus VR plus VC, but we are saying the voltage across these 2 points and voltage across these 2 points has to be, the sum of that has to be this voltage. Okay. Now what is VR over these 2 elements? It's the current flowing into the node. Right. So the current flowing into the node is equal to the voltage between these 2 points divided by the total resistance. That's what you see here. Divided by the resistance. You always can use this Ohm's law. If V is equal to IR, I would be V over R. The resistances are in series. So what do? We add them. And this is the voltage, okay? Is equal to, again, VC over 1 over CS. Because, remember this relationship. Alright? But what is VR? VR is input minus whatever voltage is being output. Right? I can write this as V LR if that makes more sense. This is nothing but VLS plus VR of S. Got it? You cannot develop a relationship for current flowing only through this element. The current is flowing through, since it's a series, the same current is flowing. And this is that the expression for that current. Current flowing into the node is equal to IR of S, okay, or ILR of S, and the current flowing is IC of S. And then you apply Ohm's law, okay. And once you apply Ohm's law, what you're going to get? V of S minus Vc of S over R plus Ls. The reason we cannot use this, why can't we use this? We don't know VLR of S. We are trying to develop a relationship between output and input. Everything has to be known on the right hand side. See, when you do this, you cannot have expressions on the right hand side where you don't know things. So when you do this, so if you look at this, now this is the input, this is the output, this we know, right? Then you move around and you're going to get the same input-output relations that we did for voltage law. Voltage law will always be easier to apply. The trick is, if you're given a simple problem, you can quickly do the voltage law. Okay? You can quickly do the voltage law and try to do your current law. If you're asked to do the current law, it will hardly take any time. Even for a very complex circuit, the voltage law will be very simple. You just have to, we'll again look at the impedance way of solving circuits. The impedance way of solving translational systems, we looked at that, right? We'll look at the same impedance way of solving electrical circuits. Using that, you can really solve these circuits easily. And then you can try to arrive at that particular solution using the current law. Got it? Are there any questions on this one? No? You good? Huh? I'll just do the rule. Yeah.
If you can model and